Today, we're talking about something that feels like it's been ripped right out of a sci-fi movie. It's called Maglev, and it's a train that literally floats. So how in the world does it work? And if it's so amazing, why isn't it everywhere? Let's get into it. Just look at this number for a second. 603 kilometers per hour. That is 375 miles per hour. No, that's not a plane. It's not some experimental rocket. That is the world speed record for a vehicle on the ground, set by Japan's SCM Maglev plane back in 2015. It's just staggeringly fast. And that, of course, leads us to the biggest question of all, the one we're going to tackle today. How can a train that has no wheels, no traditional engine, and doesn't even touch the track end up being the fastest thing on the planet? Well, the answer isn't science fiction. Believe it or not, the core idea has actually been around for more than 100 years. So we're going to break down exactly how this incredible piece of engineering pulls it off, starting with the absolute basics. The secret sauce is right there in that last part, eliminating rolling resistance. See, with a normal train, you've always got friction, the wheels grinding against the steel track. And that friction, well, it creates a natural speed limit. Maglev just says, what if we got rid of the wheels and the friction entirely? Okay, so how do you get a vehicle that weighs many, many tons to just float? I know it sounds like some kind of magic trick, but it's all pure, unadulterated physics. Let's break down the two main ways engineers have actually made this a reality. At its very core, the idea is pretty simple. You're using one fundamental force, magnetism, to fight and win against another fundamental force, gravity. You just have to create a magnetic field that's powerful enough to literally push back against the entire weight of the train, lifting it clean off the guideway. Now, there are two main flavors of maglev technology. The first is called electromagnetic suspension, or EMS. The easiest way to think about this one is like a magnetic claw on the train that reaches down, wraps around the track, and is constantly pulling itself up. The other way is electrodynamic suspension, or EDS. This one doesn't pull, it pushes. You've got powerful magnets on both the train and the track that repel each other, literally forcing the train up into the air. But there's a pretty big catch with this method. It only works when the train is already moving pretty fast. So for an EDS train, like that Japanese record breaker, the whole process feels a lot like an airplane taking off. It actually starts out rolling on regular wheels, but as it picks up speed, the magnets start generating this incredibly powerful repulsive force. And once it hits just the right speed, that force becomes stronger than gravity, and the entire train just lifts up and takes off, floating on a magnetic cushion. Okay, so let's recap. We have a train that floats. It can accelerate faster, it's way quieter, and it needs a lot less maintenance. It sounds absolutely perfect, right? Which brings us to a very obvious question. If this tech is so revolutionary, why isn't every single high-speed train on the planet a maglev? I mean, when you look at it on paper, the advantages are just incredible. Maglevs have a way higher top speed, they need way less maintenance because no parts are touching and grinding down, they're faster off the line, and they're so much quieter. Really, the only thing conventional trains have going for them is that one last point. They can use the tracks we already have. And that right there is the multi-billion-dollar problem. $1.2 billion. That's what it costs to build just 30.5 kilometers. That's about 19 miles of track for the Shanghai Maglev. So you can't just run one of these on existing railway lines. You have to build a brand new, incredibly precise and purpose-built guideway from the ground up. And that, as you can see, is astronomically expensive. And that insane cost has made the journey from a cool idea to a real-world system a very, very long one. The first working model was shown off all the way back in 1912. It then took until 1984 for the very first commercial system to open, and that was a low-speed one. It took another 2 decades after that for Shanghai to launch the first high-speed version. It's kind of always been the technology of tomorrow. So, after that century-long journey, where can you actually go to ride a maglev today? Well, given all that promise, you might be a little surprised to find out just how rare these things still are. That's it. In the entire world, there are only seven fully operational maglev systems, and they're all located in just 3 countries in East Asia: China, South Korea, and Japan. So despite all the prototypes and proposals we've seen over the decades, these are the only places where the technology has really truly taken off. So what's next? Is Maglev going to stay a super cool but super expensive niche technology forever? Or is it finally on the verge of a real breakthrough? Let's take a look at what's coming up on the horizon. And the future looks incredibly ambitious. Japan is going all in, building a massive new line to connect its biggest cities. At the same time, China is already working on new prototypes to smash the current speed records. And then you get to the really wild next-level idea: vac trains, sometimes called Hyperloop. The idea there is to put a maglev train inside a sealed tube and then suck all the air out, completely eliminating air resistance. If that works, you're talking about speeds that could actually compete with airplanes. So this all brings us back to that final big question. For over 100 years, maglev has been the shimmering promise of a faster, cleaner, more efficient way to travel, but it's always been held back by that staggering cost and complexity. But now, with some of the world's biggest economies pouring billions into the next generation, you really have to wonder, after all this time, is the train of the future finally pulling into the station?